Bismillahirrahmanirrahim. In the name of Allah, the most beneficent and merciful. Dear student, Assalamu alaikum. My name is Dr. Rana Farhat Mehmood, and today we are back with our third lecture about single crystal X-ray diffraction. This is related with our MS Chemistry second semester course X-ray diffraction technique under the course code of Chem 5134. Dear student, in this slide we are going to study about four circle or area detector diffractometer. The most common automated technique is the four circle diffractometer. The name derived from the four arc used to orient the crystal, bringing the atomic planes into diffracting position. In the figure that is coming in the next slide, the geometry of a four-circle single crystal diffractometer will be elucidated. The four circles, actually four axes, are marked as phi, x, omega and 2 theta. The 2 theta and omega angles are known as gamma and eta. A notation we will often employ in a remainder to avoid clutter and confusion with other symbols. For example, the solid angles. Here is the elucidation or the pictorial diagrammatic display of the single crystal X-ray diffraction technique, in which different kind of rotations are being known and different four circles are being observed. One is here, that is rotation symbolized by phi, and other is another rotation x, and other rotation is 2 theta, and other rotation is gamma. These are different kind of rotation that occurs in the single crystal X-ray diffraction, in which the crystal is rotated and observed by these four rotating circles. There is another elucidation in which we can see different kind of circle, one at the top denoted by phi, and other is here right on side, that is omega, and there is another rotation along x-axis, and there is another rotation which is denoted by 2 theta. These are four kind of rotation that occurs in the form of four circles, and these four circle rotation are observed in single crystal X-ray diffraction to record the diffraction pattern, and after that diffraction pattern different softwares are used to elucidate or to calculate the measurements of the single crystal bond length and bond angles, and from there we can get the information about the structure of a single crystal. Here are some machines showing these kind of rotations. Here we can see there are different kind of rotations, that is phi, omega, sigma and 2 theta. The diffractometer has an area detector and can collect a complete data set for a crystal in less than 6 hours. whereas traditional diffractometer use point detectors which measure the intensity of each diffracted beam individually in sequences. An area detector records the diffraction pattern over a large area of reciprocal specks simultaneously. The image is then stored digitally as a frame of diffracted intensity information. Many frames are collected in turns as the crystal is rotated in a series of small steps. The frames are then analyzed and the intensity of each individual reflection can be determined. Here is another pictorial diagram in which on one side we can see there is a XRD machine, single crystal X-ray diffractometer, and this is connected with the computer which uses some kind of mathematical software and which convert all the information coming from the X-rays in the form of diffraction pattern, and it calculate all these kind of diffraction pattern and give them another value which can be converted to use them in to find out a single structure of that crystal. And when we discuss about the instrumentation of single crystal X-ray diffraction, the X-ray generated uses a standard water-cooled tungsten filaments source, which produces MOK alpha radiation. It is typically used at 50 kilovolt and 40 milliampere 2 kilowatt power. The CCD charged coupled device area detector has a two-dimensional array of photodiodes that is in the form of 1024 into 1024 elements coupled by fiber optics to a light-sensitive phosphor screen. When X-rays strike the screen, light is produced, the intensity of which is measured by the photodiodes. The detector operates at minus 55 degrees centigrade for optimum signal to noise ratio, and the analog signal from the detector is digitalized by the camera known as Gandolfini electronics unit, which allows for adjustment of the detector gain and exposure times under control of the attached Pentium PC, and the data are transferred to the local network of silicon graphics computers which are used for data storage and analysis and also for structure refinement. Here is the pictorial diagram that is discussing about how the single crystal data is taken from the machine and then it is converted to the PC attached with the machines through some softwares, and from there we can take different information about the structure of the crystal that is being studied in this machine, and working of diffractors could be studied in this slide. Here we can see that X-ray diffractometers consist of three basic elements. Number one, an X-ray tube. Number two, a sample holder. Number three, an X-ray detector. X-rays are generated in a cathode ray tube by heating a filament to produce electrons. Accelerating the electrons towards a target by applying a voltage and impact of the electron with the target material. And when the electrons have sufficient energy to dislodge inner shell of electrons of the target material, characteristic X-rays spectra are produced. These spectra consist of several components, of most common being K alpha and K beta. These are kind of X-rays which are generated by different shells present in the atom, and K alpha consists in part of K alpha 1 and K alpha 2, and K alpha 1 has a slightly shorter wavelength and twice the intensity as K alpha 2. The specific wavelength are characteristic of the target material. So here is the working of diffractometer, in which three basic elements like X-ray tube, sample holder and X-ray detectors are used. From there X-rays are generated, and these are generated by heating the filament to produce electrons, and these electrons are accelerated towards the target material by applying high voltage, and the impact of these electrons is such that they can eject the X-rays from that material. When the electrons with such sufficient energy strike the inner shell of the target material, then characteristic X-ray spectra are produced. These spectra consist of several components such as K alpha and K beta, and then K alpha can be further divided into two parts, K alpha 1 and K alpha 2. The difference between K alpha 1 and K alpha 2 is that K alpha 1 has slightly shorter wavelength and it has twice the intensity as K alpha 2. The specific wavelength are characteristic of the target material. By filtering by foils or crystal monochromators, it is required to produce monochromatic X-rays need for diffraction. Whereas K alpha and K alpha 2, K alpha 1 and K alpha 2 are sufficiently close in wavelength such that a weighted average of the two is used. Molybdenum is the most common target material used to produce such kind of X-rays for single crystal diffraction, where molybdenum K alpha radiation have wavelength of 0.7107 angstrom. These X-rays are collimated and directed onto the sample. When the geometry of the incident X-rays impinging the sample satisfy the Bragg equation, that is, the constructor interference occurs, then a detector record and process this X-ray signal and convert this signal to a count rate, which is then output to a device such as a printer or computer monitor. X-rays may also be produced using synchrotron, which emits a much stronger beam. Single crystal diffractometers use either 3 or 4 circle goniometer. Dear student, these 4 circles refer to the 4 angles 2 theta, x, phi, and omega that define the relationship between the crystal lattice, the incident ray, and detectors. The samples are mounted on thin glass fibers which are attached to the brass pins and mounted onto goniometer head. The adjustment of the X and Y and Z orthogonal direction allow centering of the crystal with the X-ray beams. Here is the pictorial diagrammatic display in which we can observe different kind of circles or the angles that have been discussed in the previous slide, and we can have a look on all these kind of circles that are known as 4 circles. So this is the CCD, charged coupled device, in which X-ray beams coming from the X-ray tube along x-axis when which strike on the single crystal mounted on the goniometer here, and it is scattered with different kind of angles producing that can be seen in this figure. That is, one is circle creating with K, that is known as omega, and another circle of rotation is phi. There is another circle of rotation psi down the figure, and there is another circle which is representing as 2 theta. Now moving on, we can see that X-ray leave the collimator and are directed at the crystal. Rays are either transmitted through the crystal or reflected off the surface or diffracted by the crystal lattice. And the beam stop is located directly opposite the collimator to block transmitted rays and prevent burnout of the detector. And the reflected rays are not picked up by the detector due to the angle involved. Here we can see the schematic of 4 circle diffractometer. The angle between the incident rays and the detector and the sample can be seen here in this figure. So here are different kind of circle that we can observe, and also different kind of angles that are produced by the incident rays when they strike the single crystal, and after that these rays are scattered making different kind of circle and angles, and these are diffracted towards the counter, and also some beams are also diffracted towards the beam trap. In the next slide, there is another 4 circle goniometer Irelian or kappa geometry, which is also showing that how X-rays are produced by the anodes of copper, and these X-rays are then passed through the focusing mirror or monochromator, which convert these rays into a single beam monochromatic rays that are then directed on the single crystal present on the goniometer in the XRD machine. And these X-rays, when strike the crystal, these are scattered at different angles by striking the atoms present in that single crystals, which are located to one another at certain angles, and distance is also present in some planes. And when these X-rays, after striking the single crystal, are scattered or pass through the planes, then these are directed towards the area detectors, where these scattered rays produce some spots which are called diffraction pattern. And each kind of crystals of different elements or molecules have different kind of diffraction pattern, which can be studied by using different kind of software attached to the X-ray machines by using some hi-fi computers. So here we can see that diffracted rays at the correct orientation for the configuration are then collected by the detectors. Modern single diffractometers use CCD, charge coupled devices technology, to transform the X-ray photons into an electrical signals, which are then sent to a computer for processing. So dear student, as we know that we have studied that how a single crystal is taken and it is mounted on the monogoniometer, and how X-rays are produced from the X-ray tubes. And when all this process is completed, that is the X-rays are struck on the single crystal, and after striking the single crystal or after passing through that crystal, these X-rays, when strike the atom present in the single crystal, these are diffracted at certain angles, and these are also passed through the planes present in the single crystals, and they form a X-ray diffraction pattern on the detector. And after that diffraction pattern, there comes some data processing softwares which are attached, which are present in a computer. That computer is also attached with the X-ray diffraction machines. So here are some kind of software that process all that data to generate structural information about the single crystal. So these softwares are known as Berker application software, APEX2, and other software used, that is SHEL, SHELXTL. This is derived from the compatible with from and compatible with SHELX, the most widely used program like SHELX 76, SHELX 86, SHELX 93, and SHELX 97 to solve and refine the display of the single crystal. So these are kind of software that are used to solve the diffraction pattern and also to find out the structural information of a single crystal in which atoms are attached to one another at certain bond length and bond angles. Preparation of the data and space group determination is calculated by using the software known as SREF, and the structural solution is done by direct method and Peterson maps, in which the SHELX software is used. Crystallographic information files report is done by the software known as XCIF, and the molecular graphics using mercury and diamond software. Powerful package for both routine work and demanding research is necessary. So, structure determination of a single crystal is not a simple thing to evaluate. There are different kind of instrument, different kind of technologies, and different kind of softwares are involved to end up with the determination of the structure of a single crystal. So this is all about our third lecture about single crystal X-ray diffraction. So now we will move to our fourth lecture about this chapter, and inshallah we will come back soon with our lecture number 3.4. Till then, Allah Hafiz. Thank you very much.